the Otto cycle. I'm going to show you the Otto cycle. I'm going to show you something a little bit about the Otto cycle, and from the description here you see that the Otto cycle, this is the cycle for SI. SI is spark ignition engines, or you can sometimes call them the petrol engines. Now I'm going to show you the Otto cycle, and I'm going to represent using a diagram. And the diagram here is called, we have the PV diagram, the pressure volume diagram, and the TS. So what I'm saying is that you're going to have the PV diagram, and the PV diagram here, I'm going to show you. PV is simply pressure volume diagram. So the vertical is usually for the pressure, and the horizontal is for volume. So here is our P, here is our V, pressure, volume. So if you can recall the process for the four processes that undergoes in the engine, that is, we have the induction stroke, we have compression, power stroke, and then the exhaust stroke. Now my PV diagram here is going to look like this. I usually like my process 1 to 2 to include the compression process. This is the compression process. Now during this process, the Otto cycle, not process but the cycle, you find that the heat addition process and the heat rejection process usually are carried out at constant volume. Now after compression, this is now compression. Remember the induction stroke, I'm not going to talk much about the induction stroke, but the induction stroke is usually that process from here to here. So I'm going to call here V1 and here V2. So this is now the compression stroke, process 1 to 2. Now the heat addition process, which occurs at constant volume, is this process here up to 0.3, and then we have the expansion process, and then the heat rejection process. So it is at 0.4. So 1 to 2 is compression, and then 3 to 4 is called the expansion process. So don't worry much about my diagram. We'll understand as we go by. Now another diagram here is for the TS, or the temperature and the temperature entropy. Temperature entropy is going to be this one here. Sorry. The temperature entropy is this one, or the TS diagram. So this one is our T, and this one is our S, and again the processes 1 to 2 and 3 to 4, sorry, 1 to 2 and 3 to 4, and these processes here, I'm going to show you using an arrow. So this is 1 to 2, and then again we find that here S1 is equals to S2, and here V1 is equals to V4 and V2 is equals to V3. These are constant volume processes. So here we have the heat addition or Q in, and then heat rejection. And this one is compression. This is 1 to 2 is a compression. This one is expansion. Compression and expansion processes. This is point 3 and then to 4. So 1 to 2, and then again here S3 is equals to S4. So this is the Otto cycle processes. This is what we have in terms of diagram. So this is what we have. Now this sometimes you find that the Otto cycle is called a constant volume process because heat addition and rejection takes place at constant volume. Now the other thing you need to realize here is that the work done during this process, the work done is usually given by heat capacity at constant volume times the change in temperature, as we shall see in our examples. Now from the two diagrams we have some there are some important formulas which you will apply. We are going to compare the TS diagram with the PV diagram, like for example, and this we are going to come up with formulas which shall help us. For example, when you take T2 over T1, take T2 here over T1, this one is the same as maximum volume, that is V1 over minimum volume, everything to the power gamma minus 1. Gamma minus 1, we shall see what is gamma, and then again V1 over V2, V1 over V2 is called expansion or compression ratio. Which is denoted by small r, Gamma is a gas constant, and for air it is usually, if a working fluid is composed of air, it is usually 1.4, but sometimes you are given, sometimes they vary, but usually it is usually 1.4. So that means that T2 over T1 can also be given as R to the power gamma minus 1. Another comparison is if you have in terms of pressure, it means that P2 over P1 is equals to V1 over V2, but to the power gamma alone, which is the same as R to the power gamma. Other useful comparisons are such like you can also have T3 over T4. First of all, we had T2 over T1. Now T3 over T4 also. T3 over T4 also is the same as V4 over V4 over V3. This one is shown by using an eraser. This one is V3, so V2 equals to V3. That is why we are having that comparison, and again that is to the power gamma minus 1. And since v1 since v2 is equals to v3 and v1 equals v4 as shown here, this one should be v1 equals to v4. v1 is equals to v4. The t3 over t1 now can also be written as, so t3 over t4 is also equal to r to the power gamma minus 1. That is t3 over t4 equals r to the power gamma minus 1, and p3 over p4 is also equal to r to the power gamma, r to the power gamma. Correct. Now this is what we have, and of course you'll find that the heat addition process, that is Q in is usually given by the formula heat capacity at constant volume into, now you find that heat is added through the process 2 to 3. Now from 2 to 3, this is where we have the heat addition process. Process 2 to 3, here is where we have the heat addition process. Now the heat addition is given by the formula heat capacity at constant volume into the change in temperature, which is equals to, so you can also say that now change in temperature during this process 2 to 3, the change in temperature, you take T3 minus T2, so that that formula becomes CV into T3 minus T2, so that is the change in temperature during that process. On the same note, heat rejection becomes now you look at where is heat rejection process, that is process 4 to 1, so here is where we have heat rejection process. So the same is an equals to heat capacity at constant volume times change in temperature, and the efficiency or the Otto efficiency is usually the net work done divided by Q in, net work done divided by Q in, and we have said that work done is CV into change in what? Temperature. So we shall look at one example and see how this one comes about, now. Let's look at one example here and see how we can apply these formulas in a question. And the question is here. It says a 4-stroke SI engine has a compression ratio of 6. So from this question we are just going to slot in our values. So we are being told that the compression ratio R is equals to 6 and the swept volume is 0.15 meters cubed. Now swept volume is usually the change in volume, that is V1 minus V2 gives us the swept volume, swept volume, which is 0.15 meters cubed. The question continues by saying that the pressure and temperature at the beginning of compression are, so P1 at the beginning, we are going to have P1 is equals to 98 kilopascals. That is 98 kilopascals, and T1 is equals to 60 degrees Celsius, which is the same as you add 273, which gives you 333 Kelvin. Remember, in thermodynamics, temperature is usually given in terms of Kelvin. Now the question asks, determine the pressure, volume, and temperatures at all salient points. So at all salient points. All salient points, that means that since we have P1, we are going to get P2, P3, and P4. If we have T1 again, we are going to get T2, T3, and T4. And in terms of volume, we are going to get V1 and the values of V1 and V2. Now you are being told again that heat supplied, so that is heat input, or that is heat input Q in is given as 150 kilojoules per kilogram. Also find out the entropy change, work done, efficiency, and the mean effective pressure of the cycle. So we are going to calculate all these, work done, changing entropy, and we are given that Cp is equals to 1 kilojoules per kilogram Kelvin, and then Cv is equals to 0.7. Remember, these are constants, and then plot the cycle on a TS diagram. We are also going to plot the cycle on a TS diagram. So the TS diagram is not that hard. You just come in and draw your lines. So this is our TS diagram. So here we have the T, and here we have the S diagram, and as usual, my first process, I like it here. So process 1 to 2, I'll put it here. This is 1 to 2, and then 3, and then that is 3 to 4. So this is my TS diagram. So this is Q in and Q out, rect. And this one is compression, and this one is expansion. So that is our TS diagram. Now let's begin by saying that of course the SI engines operate on Otto cycle. And considering the working fluid to be a perfect gas, so we come and say that if we consider that the working fluid here is a perfect gas, without forgetting that always Cp, or rather the value of gamma is usually given by this formula, Cp over Cv. Now we have the values of Cp and the values for Cv. So we just slot in your values and then simplify. We are told here that Cp is 1 and Cv is 0.71, and if you divide that, it will give you exactly 1.4. It gives you exactly 1.4. Now again we have another gas constant here known as R. So R is usually Cp minus Cv, and we are given that R from the question. The value of R should have been given. Actually, that value shall use it later on. Let's first of all consider the heat supplied. We are being told that the heat supplied is equal to 150 kilojoules per per kilogram. And then heat supply, we know that that is the process from 2 to 3. If you draw the PV diagram, so we know that the heat addition process taking place through the process 2 to 3, like we saw on our notes here. Let me show you the notes. Yeah, so the heat addition process, this process here was the process of heat addition. Correct. Now let's go ahead and find out now how can we play around with this value here. We also know that the compression ratio, the value of R, the compression ratio we are given as 6, and from our previous discussion we said that the compression ratio R is usually V1 over V2, V2. Now if I can call this one our equation 1, and then I can come and say that V1 alone should be, if you cross multiply, V1 alone should be equal to 6 times V2. 6 times V2. I call this one my equation 2. Call that one equation 2. Since swept volume is given by V1 minus V2, and from the question we were given that swept volume is equals to 0.15 meters cubed. Now I can substitute my equation 2 here. I can substitute for V1, so that 6 times V2 minus V2 should give us 0.15. Now if you simplify that one, you'll get that V2 is equals to V2 alone should give you a value like 0.03 meters cubed. That is the value of V2. On the same note, now since we have V2, we can get V1. You can now get V1 using either equation 1 or equation 2. So you just substitute for V2 is equals to 0.03, and you find out that V1 is equals to 0.18 meters cubed, and of course V1 must be more than V2. Yeah, V1 must already be bigger than V2. Now we have answered now this question here. This value there, we have found V1 and we have also found V2. Now let's go ahead and try finding the value of temperature, that is T2. The value of T2. If you allow me, I'll just erase this part here. I'm going to erase this part here. Sorry for that. Eraser, where's my eraser? My eraser is messing up with me. Now, since we know that T2 over T1, from our previous discussion, we say that T2 over T1 is equals to V1 over V2, or R to the power gamma minus 1. Now we have the value of T1 that we were given in the question. We have the value of T1, we have the value of R, we have the value of gamma. So getting T2 will be very easier. So we come and say that T2 is equals to T1. T1 we are given as 333 Kelvin, multiply by the value of R, which is 6, and this one is 6 is raised to the power gamma minus 1, and gamma is 1.4 minus 1, and if you simplify that one, you will get T2 to be equal to approximately 681.87 Kelvin. It's 87 Kelvin. So we have found the value of T2. We can go ahead now and get the value of the other temperatures, and we, looking from our previous discussions, we can use the value of the heat supplied, which is 150. Heat supplied here was 150, so we can use that one. But before we use that one, if you can remember this formula, that PV is equals to mRT. Now the value of R, as I was telling you, R is given by Cp minus Cv, that is Cp minus Cv. Is that right? So that is correct. So R is usually Cp minus what? Minus Cv, and that one, if you simplify, will give you a value like 0.29 kilojoules per kilogram Kelvin. That is the value of R. We are going to use that R together with the heat supplied. Now, going back to this formula, going back to that formula, how can we get the value of M? How can we get the value of M? The value of M now becomes PV divided by RT. PV divided by RT. PV divided by RT. Now you can take P1 V1 divided by R. R is a constant, so we shall just use 0.29, and then this one is T1 to get the value of M. So P1 was given as 98, so this one multiplied by V1, which is 0.18, we found that, divided by 0.29 multiplied by T1, which was given as this one, and from there you'll find that M is equals to 0.183 kilograms. Now from the formula, from this formula here, we can get the value of temperature, that is T3, because we know that Q in is that process from 2 to 3. So Q in is that process from 2 to 3, which is the same as mCv into T3 minus T2. That is the change in temperature during that process. Now we have the value of M here is 0.183, and this one is multiplied by Cv, which is 1 point, not 1 point but 0.71, and this one is T3 minus T2. We found that it is 681.87 Kelvin, and if you simplify that one, you will get the value of, now since Q in was given as 150, remember from the question we were given that 150 is the heat supplied, so from there you'll find that T3, if you simplify that, you'll find that T3 is going to give you a value like 1838.39 Kelvin. Now you can see this temperature is very, very high, which is very true because T3 is usually the peak temperature. T3 is usually the peak temperature, and that one is evident from the PV diagram. It's very evident from the PV diagram. Now let's proceed. What else can we now find? We can find P2. We can now again try and find the P2 because we already have P1. We can go ahead and find P2. It is very tough on me. Okay. If you can recall the previous formula where I said P2 over P1 is the same as R to the power gamma alone, yeah, from which P2 you can get as P1. You are given P1, the value of P1 you are given as where is it on the question? 98. So P1, so you are multiplying 98 times 6 to the power 1.4, and if you simplify that one, it will give you a value of 1204.03 kilopascals. That is P2. From there, can we now get the value of P3 by comparing this? I don't know whether this is Charles' law or Boyle's law, whereby P3 over P2 should be equal to T3 over T2. That is comparison in terms of pressure and temperatures. And since we have now P2, we have P2, we have T2, we have T3, the peak pressure we found, yeah. So we have T3. So all those values we are going to use in order to get the value of P3. So if you just slot in the values from which P3, this one should give you, you multiply this one, T3 times P2 divided by everything divided by T2, and our value of the T3 we found to be 1838.39 Kelvin. Multiply that one by P2, we just found it, that is 1204.03, and everything divided by T2, which was found to be, let me just confirm, T2 was confirmed to be 681.87 Kelvin. Now if you simplify that, you'll find that P3 is equals to 3246.19 kilopascals. Let me find a space here before we continue. Now next thing we are going to do here is try and get now the values of T4, P4, yeah, because in terms of temperature we are left with only T4. Other values have been already found. Correct. Now we can come and say, I use the other comparison, that is T3 over T4, which should be equal to the value of R, just like we had discussed earlier, to the power gamma minus 1. This is gamma, not R. And from here we can get the value of T4. Now from here, this implies that T4 will be equal to T3 divided by that one, power gamma minus 1. Just slot in your values, and from there we have T3 we found to be T3 was found to be how many? Let me just confirm. 1838. 1838.39, and this one divided by 6 to the power 1.4 minus 1, and that one should give you T4 is equals to 897.79 Kelvin. On the same note, we can go ahead and find the value of P4. We can go ahead and get the value of P4, from which P4 should be P3 divided by 6 to the power 1.4, and from there, because we had P3 to be equal to 12 P3 3246 3246.19, and we're going to divide by 6 by 1.4, which gives us a value of P4 from your calculator to be equal to 264.22 kilopascals. Now let's go ahead and calculate the entropy change, because we have found the volumes V1 and V2. We have found T2, T3 and T4, same as pressure, that is P3, P4 and P2. Now the entropy change, which can be either S3 minus S2 here, from 2 to 3. From 2 to 3 we shall have S3 minus S2, and S3 minus S2 is the same as S4 minus S1, because S1 is equals to S2 and S3 is equals to S4. Yeah, so that entropy change is usually correct. So change in entropy is usually given by mCv ln T high over T low, highest temperature over the lowest temperature. Now this implies that you can calculate the entropy change here in two ways. You can either take mCv ln, you can either take now T4 over T1 or mCv into T3 over T2. You will still get the same answer. So if I pick this one, so entropy change will be given by the mass was 0.183 times CV. CV was given as 0.71, and then this is multiplied by ln 897.79 divided by T1 was 333 Kelvin, and this one will give you 0.1289 kilojoules per kilogram. Now you can also try it using T3 over T2. You can also try it using T3 over T2, and you find that you'll get the same answer. Let's proceed to get the amount of heat rejected, and we say that heat rejection takes place through the process 4 to 1. So you come and say Q out is given by mCV into the change in temperature, that is T4 minus T1, and that one is equals to, we just slot in your values, times 0.71 into 897.79 minus 333 Kelvin, and this one will give you 73.38 kilojoules per kilogram. Now net work done, the net work done now is the difference between heat in and heat out. So these are heat in minus heat rejected will give you the net work done, which is equals to 150, as was given in the question, minus 73.38, and this one gives you net work done to be 76.62 kilojoules per kilogram. And the other question is asking about the mean effective pressure, which is given by the formula net work done divided by clearance volume. This is 76.62 divided by the clearance volume from the question was given as 0.15, and this one gives you a total of 510.8 kilopascals. That is 510.8 kilopascals. And then lastly, the efficiency, the Otto efficiency, becomes now the net work done divided by heat given into the system, which should give you just slot in your values. So we just take net work done divided by the heat given into the system, which was 150, which gives you 0.511, which is the same as 51, approximately 51%. So this is how you go about solving such a problem.